The purpose of commercial transport aircraft is to fly as fast, but at the same time as efficiently as possible. We have seen that most of the adverse effects of high-speed flight begin when flying faster than mcrit. So if mcrit can be increased, a higher true airspeed is possible while maintaining the same level of efficiency. The unfavourable characteristics of high-speed flight, such as Mach tuck, high-speed buffet, and wave drag, are grouped under the heading of compressibility effects. There are several methods of increasing mcrit, the first of which is the thin wing section. A thinner wing increases the cross-sectional area of the streamlined flow. This results in a reduction in local velocity. Therefore, mcrit is increased. Unfortunately, a thin wing has some disadvantages. Namely, less lift is produced for a given angle of attack, the structural weight is higher, and there is an obvious reduction in the size of the fuel tanks. With these disadvantages in mind, the designers will provide jet transport aircraft with a wing as thin as is practical. A swept-back wing is the most commonly used method of increasing mcrit. Sweep forward would give the same benefit, but forward sweep is structurally unsound, so generally speaking, has only been used on a few experimental aircraft. Consequently, any references to a swept wing means swept back. The only reason a swept wing is fitted to an aircraft is to increase the critical Mach number. A swept wing also has some associated byproducts, some favourable and some not, which we'll look at later. Observe, the effective airflow passes over a straight unswept wing at 90 degrees to the leading and trailing edges, giving a certain effective chord. On a swept wing, the effective airflow passes over the leading and trailing edges at an angle, which gives an increase in effective chord. This results in a decrease in thickness chord ratio, which has the effect of increasing the length of the stream tube. Thus, the local velocity is decreased, and therefore mcrit is increased. And vice versa. Anything which causes an increase in local velocity will decrease mcrit. For example, a downgoing aileron. To illustrate some of the advantages and disadvantages of a swept wing compared to a straight wing, we can use the lift curve. A favourable byproduct of a swept wing concerns flight in turbulence. Here we can see an angle of attack that results in a certain lift coefficient. If a gust increases the angle of attack, the lift coefficient will increase. If we now reset the graph, we can consider the lift curve of a swept wing for comparison. At the same angle of attack, the lift coefficient of the swept wing is less than that of a straight wing. But because of the reduced lift curve gradient of the swept wing, the same increase in angle of attack will result in a smaller increase in lift coefficient. Therefore, one of the favourable byproducts of a swept wing is that it is less sensitive to changes in angle of attack due to a gust or turbulence. Let's now consider an unfavourable byproduct of a swept wing. Illustrated is an angle of attack that gives the required lift coefficient from a straight wing. To obtain the same lift coefficient from a swept wing requires a higher angle of attack. The disadvantage to an aircraft with a swept wing is that it must fly with a noticeably higher nose attitude at low indicated airspeeds. This complicates landing gear design, including the possibility of tail strike when taking off and landing, plus reduced visibility from the flight deck. Another unfavourable byproduct of a swept wing is that the maximum lift coefficient is reduced when compared to a straight wing. This results in a higher stall speed, thus increased takeoff and landing distances. The two major disadvantages of the swept wing, pitch up at the stall and Mach tuck, have been covered elsewhere. We have seen that some of the problems of high-speed flight are associated with airflow separation behind the shock wave. As you learned when studying stalling, if the kinetic energy of the boundary layer is increased, separation will be reduced. Boundary layer kinetic energy can be increased if vortex generators are fitted. These are small blades projecting from the surface. Each blade generates a small but intense vortex, which re-energizes the boundary layer and reduces shock-induced airflow separation. A written exam question may use the wording, vortex generators induce high-energy air from the free stream flow to mix with the boundary layer. A further disadvantage of a swept wing is the reduced effectiveness of trailing edge control surfaces and high lift devices because their hinge line is swept. Let's summarize the relevant facts about a swept wing. Its purpose is to increase the critical Mach number. Its advantages are: it gives a positive contribution to lateral static stability, a positive contribution to directional static stability, and decreased sensitivity to gusts and turbulence. Its disadvantages are: pitch up from its tendency to tip stall, with the attendant possibility of deep stall or superstall, Mach tuck, a higher stall speed and consequent increased takeoff and landing run, less effective trailing edge control surfaces, particularly the trailing edge flaps, and lastly, a higher nose-up attitude at low indicated airspeed. Just as a matter of interest, the sweep angle for a jet transport aircraft is approximately 30 degrees, measured from the quarter chords line to a line perpendicular to the root chord. Our study of shock waves has concentrated on those on the wing, usually the place where supersonic flow first occurs. But a shock wave will form wherever the local velocity exceeds Mach 1. There will be a local airflow acceleration wherever the cross-sectional area of the streamline flow is reduced. So, at transonic speed, there will be shock waves at various locations on the aircraft, in addition to those on the wing. Wherever there is a sudden change in the cross-sectional area of the aircraft, from nose to tail, shock waves will form and add to the wave drag of the aircraft. To minimize wave drag, there is an ideal rate of change in cross-sectional area of the whole aircraft, from nose to tail, which is called area rule. But this shape is not practical because of the need for a wing, tail surfaces and engines, which will unfortunately give rise to sudden changes in the cross-section. Aircraft must be carefully designed so that items with a large cross-section, like the wing, are positioned at the widest area of the fuselage, and that the cockpit, tailplane, engines and other bumps are spread out along the fuselage. For aerodynamic and other reasons, the ideal area rule is not possible, but by clever design a good compromise can be achieved. Engine position can be optimized. Even the swept wing helps with area rule. Flap tracks and their operating mechanisms have to be streamlined, but the shape and length of the fairings is optimized to take advantage of area rule. But by far the greatest contribution to area rule is the design of the wing root fairings on modern jet transport aircraft. The designers of military aircraft don't have to make so many compromises with area rule as do the designers of transport aircraft. Here, the ideal cross-sectional area distribution is shown. And this is the actual cross-sectional area distribution of an aircraft with no area rule incorporated in the design. When area rule is incorporated in the design, the actual distribution of cross-sectional area is much closer to the ideal, and consequently, wave drag is minimized. You can see that the designers have reduced the cross-sectional area of the fuselage where the wing is attached. This is obviously not possible on a transport aircraft. A wasted fuselage resembles a conventional Coke bottle, and you may see references to Coke bottle shape in questions relating to area rule in the written exam. A common design element used to increase efficiency when operating in the transonic speed region is the supercritical aerofoil. A conventional aerofoil section is shown for comparison purposes. Here is a supercritical section. At first sight, it looks a bit odd, but it is only towards the wing root that the shape is as obvious as this. When compared to the conventional, the supercritical section has a blunt or well-rounded leading edge, greater thickness, a flat upper surface, and a thick trailing edge. Because the airflow doesn't accelerate as much over the flat upper surface, the formation of shock waves is delayed to give a higher M-crit, and the shock waves are much smaller and weaker when they do form. So the advantages of the supercritical over the conventional section are less sweep angle required, greater stiffness, and greater fuel capacity. The extra fuel capacity will allow a greater payload to be carried over the same distance, or the same payload over a longer distance. The disadvantages of the supercritical over the conventional section are more complex high-lift devices are required, there is more trim drag, and if the aircraft experiences high-speed buffet, any oscillations will be more severe. None of the disadvantages outweigh the advantage of a higher critical Mach number. So all jet transport aircraft will have a wing with a supercritical section.